Right, so let's talk about ELMo, or embeddings from language model, which is what the acronym ELMo actually stands for. So ELMo is a paper that came out 2018, and it is authored by a couple of researchers from the Allen Institute for Artificial Intelligence. ELMo is noteworthy, I believe, because it was one of the first approaches that came out that tried to make image-like transfer learning, image model-like transfer learning possible for NLP, and it did so in quite a clever way, in my opinion. And before looking a little bit more closely into ELMo, I want to encourage you to have a look at this paper. NLP papers, let's be honest, they can be somewhat hard to read. If you look up, for instance, papers that appear at NIPS, which is maybe the flagship conference in AI, I suppose these papers can give you quite a hard time. This paper is very readable, very, very clear, very approachable. And as I said, the authors around Peters et al., they put forward some really cool ideas to facilitate that, transfer learning for NLP. So let's have a look into the unique features of ELMo and how these are made possible. Embedding from language model, as I said. So they use a language model to construct the word embeddings. Language model, you've seen them long ago in our sessions on RNN. That was our first encounter with language modeling. And more recently, you looked into BERT, GLUVI, fast text, these classical word embedding techniques. And now these two worlds come together. BERT, for example, there was a shallow feed-forward neural network. And fast text was a bit like that, in just going to the character level. GLUVI, started from a different approach, but worked in a similar manner. And none of these techniques, neither BERT, nor GLUVI, nor fast text, nor others, used the RNN as their underlying vehicle. So does ELMo. That is one factor that puts it apart from the previous approaches. It comes as a deep model. I put the deep, I highlighted the deep. It was a deep model, but not too deep in terms of the number of layers, as we shall see. ELMo is nothing like what deep is in the scope of computer vision, where we have models with like 150 layers or so. ELMo, in fact, uses 2 LSTM layers and an embedding layer. So pretty shallow for a deep model, but compared to BERT, for example, that clearly was a deep model. But actually the unique selling proposition, to talk marketing here, is that ELMo embeddings are contextualized. Deep contextualized word embeddings. They're deep, but they're also contextualized. And this little cartoon here is to show you what contextualized means. We have Kermit here asking, hey ELMo, what is the representation of the word bank? And then instead of just, outputting a bunch of numbers, which is the word embedding of the word bank, that is what BERT would do. That is what GLUVI would do. They give you the embedding of the word bank, which is derived from analyzing large corpora. ELMo, however, is different. So here our little ELMo would ask, give me some context, and then Kermit goes, I'm your body, you can bang on me. And then ELMo says, okay, so the embedding is such and such. And let's imagine Kermit says, I need to go to the bank, draw some money. Then ELMo would have given Kermit a different embedding. And this is the meaning of contextualized. So what I'm trying to say here is that ELMo would not really recognize, or would maybe not understand, the difference between the financial institution bank and the thing you sit on, or here you can bang on me. What ELMo really is doing to take away a bit of this magic with which they sell this contextualized embedding thing, ELMo would just analyze the whole sentence this way, looking for the context of the word bang and in which it appears, in which it is used, and then output an embedding. That is what ELMo actually does when saying, I'm giving you contextualized word embedding. It looks at the whole sentence and then creates an embedding on the fly that matches this sentence. And to look a little bit ahead, if you remember what we discussed in the scope of recurrent neural networks, that actually makes sense that an RNN-based language model would receive a sentence, then process that sentence token by token, word by word, and each time update its hidden state. That, sort of fits together. I hope you agree with that. I hope you also feel, that somehow fits together. That by analyzing the whole sentence, it's easier to make sense out of the words that appear in that sentence compared to just looking at words individually without the context. And that is exactly what Word2Vec does, and Groovy. They derive the embeddings from looking at context, of course. Word2Vec has this window which is slides over text trying to predict the center word or the context words from the center word. We've seen that, but once you're done with the training, the embedding is just fixed. And that is different in ELMo. So from a motivational point of view, the authors argue in their paper that if we are to derive a good word embedding, then on the one hand, we need this embedding to capture these complex characteristics of word use. And this means syntactical patterns, how different grammatical structures reoccurs in sentences and needs to be obeyed, but also the semantic, the subtleties of text, as here in the word bang. What does that really mean? It's used in many contexts. And that's both of these a good embedding should somehow embody. And in addition to that, a good embedding should also capture how these complex characteristics, semantics for instance, how this changes with the context in which words are used. That is the promise. So I hope I managed to interest you in ELMo. Let's try to look what it is doing under the hood. ELMo vectors, they originate from a deep bidirectional language model. So we need to revisit a bit of what we discussed in our two RNN lectures. We have a deep model that is bidirectional. So let's revisit what that means. Depth in the context of an RNN, in the context of a recurrent neural network, and bidirectional. Oops, sorry, that was unintended. Where are my slides? Slides back, I need you. Here we go. Okay, sorry about that. I'm showing you here a deep bidirectional RNN, recurrent neural networks, which emerges from a combination of stacked RNNs, where you just put RNN layers on top of each other to make them depth, not only in the temporal dimension, but also in a more classical meaning of depth, as in many layers. You just stack them one on top of the other. And on the right-hand side, we have bidirectionality, where we said that a normal RNN language model would take a sentence and then process it from the left to the right, at least in the type of languages we used to think of that are actually read from left to right. Not all languages are read from left to right, as you know. Anyways, that's the sort of forward processing. You try to predict the next words in the sentence from left to right. Given the piece, let's say the lecture was, the language model tries to figure out the next word in that sequence, which in my example is the word terribly. That is a classic language model. And bidirectionality meant that we sort of reverse the processing. We still process the same sentence, but not from left to right. Instead, we process it right to left. So in this example, the back word RNN, it would start with the input token exclamation mark, process it, calculate some hidden state, and from that we would train it to predict the word exciting. And then from the two words exclamation mark exciting, we would train our backward RNN to predict the word terribly. So just an ordinary RNN, but processing all the input sequences in reverse order. And then the bidirectional RNN is just an RNN which does both in parallel or combines these two RNNs in one, meaning that you concatenate the hidden states that you calculate. And that is what the graph shown here on the right hand side is to convey. You have the forward path, you have the forward RNN, which for each token that you input gives you a hidden state. You have the backward path RNN, which also gives you a hidden state for each token that you input. And then you just concatenate these two hidden states. And that's your full hidden state in the bidirectional RNN. And from that full hidden state, which is this layer here, pen, come on, right? That's just the concatenation. You see the color coding. I think it's fairly intuitive. You have these hidden state vectors. You have one for the forward path. You have one for the backward path with an individual activation per processing step, per token. You concat these, and then from the result, from this enlarged concatenated vector embedding, no, that's actually wrong. It's not an embedding. It's a hidden state vector. You calculate your forecast. And now a deep bidirectional RNN, as that used in ELMo, is just the combination of these two. You combine the two pictures and then trying to combine them, the result could look somewhat like that. Trying to orientate ourselves, we have tokens as inputs, words as in the lecture was terribly exciting, exclamation mark. And yeah, now you are certainly aware of the fact that we do not input our tokens as text, but rather embed these. So here we would actually have some embedding. An embedding layer. Then, however, we have our bidirectional LSTM layer with forward path and backward path, giving us hidden states, one per token. And then we stack on top of that another bidirectional LSTM, which receives as input the concatenated hidden state from the lower level LSTM. So if this is the first level, let's say RNN. You know, it doesn't matter. You can build this architecture with any type of RNN you like. And as we discovered, traditional, vanilla, recurrent neural networks don't work. They are typically unable to overcome the vanishing gradient problem. In practical application, you would always use either an LSTM or a GRU. For ELMo, they used LSTMs. They could have used GRU. Instead of that, you could implement ELMo using the GRU as well. Generally, these cells I am depicting here, you can use any RNN cell you like. Typically, it's either the LSTM or the GRU. Okay, now back to the picture. We have our first level RNN, and then here this is the second level RNN. And then, yeah, we also have a third level RNN, as already said. So that's the third level. As already said, ELMo would not even use that third level RNN. So ELMo would end here. That's the end of ELMo. But you could, go beyond that. You could grow it deeper if you wish. The point is just that looking at the first level RNN, it becomes very clear. You have these recurrent cells with their inner mechanics that we examined in quite some depth. You know how they work. And they receive an input, produce or calculate a hidden state, and from that you can derive an output if you wish. And the hidden state is forwarded to the next processing step. And for the second level RNN, well, it's just the same, only that the input is not the raw input anymore. It's not the raw embedding or the raw token. Instead, the input to the second level RNN is just the hidden state which comes from the first level RNN. We will try to build these monsters in the practical, but conceptually it's actually easy. You have this RNN cell, and you give it an input, which can be the raw data, but it doesn't have to be the raw data. You could also give it the output of a lower level RNN, or more generally, the output of some other model that you use underneath. And then you feed your RNN with that output. This is how stacked RNNs work. And if you want them to be bi-directional, no problem. That's possible. And these models are then, they are trained. I mean, God, there are a lot of parameters, right? You can decide how big you make these layers, how many units you have, and the number of units will then determine the number of free parameters that you have to train. Typically, these models are pretty big. I'll show you some numbers later. And all these parameters you can train in an end-to-end fashion. This is, by the way, this is not a language model. And you can test yourself. That is not a LM. You can test yourself whether you are able to spot why this is not a language model. If you followed along carefully, you will know how this could not be a language model. Just by the way I draw the picture. The pictures are meaningful. They are not only colorful, they are to convey meaning. There is a lot inside them. And okay, I was babbling enough to give you time to think about it. If you haven't come up with an answer yet, and you don't want to know the answer, just fast forward. The answer would be that the output layer here is just showing you a single output. That's not what language modeling is about. Language modeling is not about giving you one output. It's about predicting the next word in a sequence. So we can change the picture, and I will do so in a second, so that it really shows you an architecture for language modeling. Here the point really was to showcase the structure of a deep bidirectional recurrent neural network. The structure of the output that you stack on top of this deep bidirectional RNN depends on what task you are approaching. And if your task is language modeling, which it is in ELMo, then the output should be like shown here, where we have one prediction per processing step. And we pull from the corresponding hidden state. And this prediction is to forecast the next word in the sequence. From inputting the word the, we would try to predict the word lecture. And in the training of this network, we would calculate the log loss of our prediction for the word lecture, and whatever the deep bidirectional RNN has outputted as P of x1. Oh, by the way, before going any detail, when revisiting the slide, I thought, the notation is maybe a bit misleading. This guy here, that worried me a little bit. And indeed, if the input is x1, which is a token, or the embedded picture of a token, a word, if the input is x1, then in language modeling, the forecast should be x2, or P of x2. The probability of the word lecture. And notation-wise, you will probably want to denote that as P of x2. But actually, that would not, this argumentation does not work out if you think about the backward path, where your input x6, for instance, and then your output for the backward path should be P of x5. So what I'm trying to say is, no matter how you pick your notation for the bidirectional LSTM or for the bidirectional model, I would not know how to get it right without introducing too many indices and superscripts. I just left it like that. And you, when looking at the slide, will just please interpret P of x1 as the forecast that the model produced in the first processing step. And if anybody has a better idea how to do the notation, or seen found some nice sources where they have a better idea which is clearer, I'd welcome any comments. For us, we just note that a deep bidirectional language model gives us a forecast at every processing step for each token that you put in. You get a forecast which is to represent the next token in the sequence. When you go from left to right or right to left, it's the next. And using that output, you can calculate a loss. And using that loss, you can do backpropagation just as usual. Of course, if we were to write down the equations, that would be a pain. And we will not do that. But conceptually, it works just as backpropagation through time. No changes here. Okay, now, the important bit, I believe, that is worth mentioning is that our language model here, our deep bidirectional language model, it builds these embeddings for tokens. And if we consider the word terribly, for example, let's consider the word terribly, which we have here. That's terribly. And where in the picture do we find the embedding of the word terribly? The embedding is a vector representation. Again, pause for effect so that you can ask yourself, wow, where do I see that? Actually, multiple places. You see it here. That's the first layer embedding of terribly. And here we have the second layer embedding of terribly. And in my picture, which is a bit more complex than ELMo, we have a third layer embedding of the word terribly. So we have, in this example, we have 3 versions of the embedding of terribly, not counting the representation of terribly in the embedding layer. Strictly speaking, we would have yet another vector representation or embedding of terribly, which is the raw embedding of the word. And as far as the 3 RNN-based embeddings are concerned, these that I have highlighted, note that they well, let's write that down, or let's try to write that down. The embeddings, plural, that's important because we have multiple embeddings of our token of terribly. They encompass, they capture, they know about the left and also and the right context. And by context, again, by context I mean what other word appeared in the context window of terribly. Our embeddings, because they are bidirectional, they do know which word occurred before terribly. They have information about the lecture was, which is baked in the forward path embeddings. This lighter purple, this is light purple, not sure it is. Let's say it is light purple. And then the backward path is the dark purple balls. These, or this part of the embedding, includes information about the word exciting. And also the exclamation mark, which then maybe language-wise could just emphasize, further strengthen the word exciting. And that is really important. Well, each of these stacked embeddings has this information, each of the three I've highlighted here, each of the RNN ones. And, well, you can speculate a little bit. Exciting as a context changes the otherwise negative meaning of terribly into something good. It changes the semantics of the word terribly. And from the forward path, we know about this with was. So we have information about tense, and maybe information that something has happened before. Or you could also make the point that we have seen the was as a verb, which indicates that now we need a sort of adjective form here. Combining the forward and the backward path, we know that between was and exciting, probably we will find an adjective. So we also have syntactic structure. That's what I'm trying to say here, right? You have syntactic, but also semantic clues that you bake into the embedding of the word terribly. And that is new compared to Wörterweg and others, because these other embeddings were lacking the recurrent structure, where you compute the context when you receive a sentence. Again, jumping ahead, embeddings you use. Well, let's remember our context. Our context in the lecture is we want to do NLP transfer learning. We learn something on some text, and you reuse it in a downstream task, in a downstream application. That is our context. And embeddings is something we can reuse. We can train them on some big corpus. We can then reuse them for downstream applications. This is exactly how Wörterweg and Groovy work, how they are used. With these ELMo embeddings, things change a little bit in that we would pre-train our deep bidirectional language model and store all the weights to have this language model. And when we then use it in a downstream task, when we use it to do, let's say, sentiment analysis, when we apply it to our target corpus, the embedding of the words in our target corpus, they do not come from just going into a big hash table, pulling out the word embedding for each word, That's how Word2Vec works. Word2Vec works, yeah. With ELMo, it's different. We feed our target text through the deep bidirectional language model and calculate the embeddings. We calculate them. We don't look them up. We calculate them on the fly or during the processing of our target text. Much different, and equipping the model with the ability to recognize the context of a word. Unlike Word2Vec, where you have one embedding for bank. And then you have maybe additional embeddings for phrases. You have one for big, one for data, and a third embedding for big data. Yes. But all these embeddings are fixed. And ELMo computes these for the target corpus in awareness of the context. Let's be a bit more formal here. I'm trying to familiarize you with some of the notation that you will find in the paper, should you consider reading the paper, which I was recommending you. We have our bidirectional language model with its forward path and the backward path. Both of these paths are standard language model, so you see the equations that we used before in previous lectures. Language modeling is about predicting the next word in a sequence, so you have the joint probability over the target word, target token xi, given previous tokens 1, 2, 3, all the way to xi minus 1. That is the forward path. And in the backward path, you just need to change the notation, where you also have the conditional probability of xi that you calculate, but your inputs, what you condition on, is the right context. Xi plus 1, xi plus 2, all the way up to xn. And capital N here is my sequence length. If I have a sentence with 10 words, capital N is equal to 10. That's how to read this. And doing these calculations step by step, assuming conditional independence, this is how we calculate the joint probability of all the tokens appearing in text together for the forward and the backward path. And that's what we obtain from our stacked bidirectional LSTM. And here you see this too. So ELMo is not that deep, has just 2 layers. In these LSTM layers, and indeed ELMo uses LSTM cells, each of the cells have 4,096 units, computational units, or nodes if you wish. And I'm reusing the notation from the paper. This is why I denote vectors with arrows, and also to distinguish the hidden state vector from the forward and the backward path, because in the bidirectional LSTM we have these 2 hidden states. Both are denoted by HIL. I is the input token. We have one hidden state, right? So here we have I equal to 1, and we also have L equal to 1. That looks very much like an E. Apologies. Is that any better? Maybe. And here we have I equal to 1, but L, that's maybe an L, equal to 2. And why not using this? L equal to 3 and I equal to 1. And then it goes on, right? Here we have I equal to 3 and L equal to 3 and I 3 and L 2 and I equal to 3 and L equal to 1. It wasn't that complicated. Why am I spending so much time on that? That's how to read these symbols here. That is HIL, where HIL is a combination of HIL forward and HIL backward, forward and backward path. That's the hidden state. And ELMo has 2 of these, right? Remember, that's... I was drawing this picture once and then probably was too lazy to update it for ELMo. In ELMo, the third LSTM layer does not exist. Actually, maybe it does in some versions of ELMo. I don't know, but originally it was just 2 layers. The output, the hidden state of the top layer, which is then HI capital L, that's the top layer. So this one here, that's HI capital L. From this top layer output, we typically pull our forecasts out of this layer. We use interesting point. We use only the top layer RNN or LSTM. That hidden state we use to compute our forecasts. We do not use any information from lower LSTM layers normally. And in my picture, need a new color. When we look at the forecast, we have this softmax layer, a dense layer, fully connected layer where we put a softmax in order to obtain a probability distribution over words as our output. But you know, there is nothing from, let's say, I wanted red. What did go wrong? There is nothing like that, which you could imagine. You could imagine that when you calculate your forecast, you could imagine that you also use information from the hidden state of lower layers, but normally you don't do that. In a stacked LSTM, you would not use that. You would normally just use the top layer. And we have weights in the LSTM layer. These are unique to each layer and each path. So the forward path in a LSTM layer and the backward path, they have different parameters. They have their own weights. But the weights in the embedding layer, these weights here, that are the weights that you need in the embedding layer in order to project tokens into their numeric representation as in VertiVec. And in this softmax layer here, you also have weights that you put on top of your RNN to connect the hidden states to all the output tokens representing the words in your vocabulary in a language model. Bunch of weights there as well. And or maybe why not doing it like that? That's nicer. So here we have also weights. I'm changing my color into blue. And then I can make it a bit clearer that, you know, these are the softmax weights. And these are the weights that we have in the embedding layer. And these are shared. I'm feeling a little bit playful tonight. Weights, here we go. Shared weights. By shared, I mean they are shared between the forward path and the backward path. If you imagine these paths as individual LSTMs, then they both use the same weights in the softmax layer and in the embedding layers. Whereas for the proper LSTM layers, the weights are not shared. The forward and the backward LSTM have their own weights. And for the training, ELMo uses the log likelihood loss, the log likelihood loss function, log loss, which is basically just the negative of the sum of the forward and the backward path. Right, we have forward. Which color is left for me? That maybe. Here we have our forward. Our forward path, where we have this probability distribution over words. And here we have the corresponding loss part. And we also have our backward path. And here is the loss corresponding to the backward LSTM, where we have this conditional probability distribution, our predictions, based on the context, which goes from the first token in the sequence to the, well, the last token before making the predictions, x minus 1 in the forward path, and same but in the reversed order for the backward LSTM. We have these conditional probabilities that we produce as forecast from our language model. We have parameters, the embedding parameters, the weights in the softmax layer, and all the weights in the LSTM layers, both for the forward and the backward path. That are these theta vectors with the arrow, apologies, wrong pronunciation, arrow. I need to reuse colors now. I have no fresh colors here available. I'm talking about these guys here, right? This guy and this guy. That are the weights that we have in our forward and backward LSTM. For LSTM, you will hopefully remember these are these gated cells where we have input and output, and for gate, all neural networks, many weights to be found in these gates, and we have the hidden state and the self state, yet more parameter, a lot of parameters that we have in these yellowish highlighted parameter vectors, and theta E is the embedding and theta S is the softmax weights from which our probabilistic forecasts depend, and then the log of that in order to get rid of the product and the joint probabilities. And this gives us our loss function, which we can minimize using backpropagation through time to train this language model, this deep bidirectional language model, this ELMo thing. And now, how do we use this as a mechanism for transfer learning? That's the question. So what ELMo basically does, it, in a nutshell, combines everything. First of all, we pre-train this deep bidirectional language model on some big corpus. That gives us weights. All the weights we had before, this theta E, theta S, and the theta LSTM forward and theta LSTM backward as symbols for millions of parameters. We train them on some large corpus, train our network, our deep bidirectional network to perform language modeling. That's what we do, and then we have these weights. And then we face some downstream task where we want to use ELMo. Could be sentiment analysis, could be some other NLP task. Whatever it is, in our target task, we also will use some model. Typically, we will also use some deep type of NLP model. Let's call it our target model. So how do we get our embeddings into our target model? Now, to see this, let's first revisit the way in which ELMo aggregates all the information it has produced during the pre-training part, where you train it for language modeling on some big corpus. In a nutshell, ELMo computes a linear combination, a weighted linear combination of all the embeddings it has produced for a given token or for a given word. Oh, by the way, I did not emphasize that, and on the risk of forgetting, ELMo does not start from a word embedding. Instead, it starts from a subword embedding. So this layer here, the embedding layer in ELMo, and now I'm certainly ruining the picture. This embedding layer in ELMo, it's not like Word2Vec, it's a bit more like fast text. It's not fast text, but it's the same idea as fast text. They embed subwords, not words. Sorry, I forgot to highlight that earlier on. It's important though. For each of the tokens, ELMo has multiple embeddings available. It has the raw embedding that it uses, the raw subword embedding, which is in the case of ELMo based on a convolutional neural network. And that is here I'm not using so many colors, so I'm more free in my choice of colors. That's basically I call it the raw embedding. Of some token in ELMo. It's the lowest layer if you wish. And then we have, since ELMo is a two-layered bidirectional LSTM, we have the first LSTM layer. Yeah, and guess what? We also have the second LSTM layer. And remember, we have these hidden states for each layer and each token in the deep bidirectional language model. And we can denote these by HI and then L representing the layer and I representing the individual token. We calculate these hidden state at the token level. So these guys here are our hidden states calculated at the token level. You also see three parameters here, S0 task, S1 task, and S2 task. These are just scalars, more parameter. These are called or considered task-specific parameters, task referring to the target task, be it sentiment analysis, question answering, machine translation, you name it. They are specific to the target task. And so is gamma task, which is yet another parameter that they introduce. If you look at this picture, it's maybe a weird way, but it's just my way to represent a weighted average. The average over the embeddings of our tokens, HIO, HI1, HI2, we weight these individually. We're using S1, SO, S1, S2. That gives us a weighted average, and then we introduce yet another parameter, which is gamma, that allows us to scale the result of the previous calculation. Gamma is a scaling parameter. And then trying to summarize all this, I am introducing here a function f of Ri, which is basically the information encoded in the pre-trained ELMo language model. Just to make sure, here are the formal information. Ri is vector where all the information from ELMo comes in. It's the embedding, the raw embedding, the first LSTM embedding, and the second LSTM embedding for each of the tokens together. And this other bit here in the function f, one input being Ri, the other input being theta task. Theta task is just, that's actually just the set of gamma task and then S L task. It's these 4 parameters: gamma task, SO, S1, and S2. That's the notation. And again, I'm borrowing that notation from the paper. If you wonder why does it have to look so complicated, not my decision. It's to prepare you for reading the paper. And then you will see this basically, and you will know exactly what it's about. And that together in the reminder I will call ELMo I task, which is the pre-trained embedding for token I from ELMo. And this pre-trained token I and ELMo embedding goes into our task model that performs the target NLP task, whatever that is: sentiment analysis, question answering, machine translation, named entity recognition, whatever. And that's shown in the next slide. So you just use the text embeddings that you would normally start from when you approach your target task. If you do sentiment analysis, you have, let's say you have a bunch of tweets. And the words in these tweets, before putting these into a model, you would embed them, right? Okay, maybe you use Word2Vec. You could use Word2Vec, why not? You could use some other way to embed the tokens in your target corpus, in your tweets. I denote this embedding, whatever it is that you use, with EI. It's this bit here. That is to say, when we approach our target task, we would just embed our text somehow. And then in addition to this somehow, we add the ELMo embedding. That is how ELMo is used in downstream applications. ELMo is these neural networks are pre-trained, and then the embedding from this pre-trained network we use as auxiliary input in our target task. And this is what the picture is trying to show. As input we have the sentence ELMo in action with its 3 tokens x1, x2, x3. For simplicity, let us forget about the fact that ELMo uses subword embeddings and that the task model might also use subword embeddings. Let's say we just have a bunch of tokens. In my example, ELMo in action, these are our 3 tokens, x1, x2, x3. And we embed these. And so this gives us the embedding representation, or the numeric representation of these words, ELMo in and action, E1, E2, E3, using, for example, Word2Vec. That's important, to your target text, to your sentences that you are now about to process. You run the deep bidirectional language model, you run ELMo without training. ELMo is pre-trained, you just apply it. You basically run all your text from your target corpus through ELMo. That's the red part in the picture. You see these red arrows here. Every token goes into the pre-trained language model, goes into ELMo. What will happen if you put your text to ELMo? Well, you embed the tokens in the ELMo specific way. You do these character level embeddings or subword embeddings. Then you feed this to the first bidirectional LSTM layer, calculating hidden states for every token, the output of the hidden states for every token or processing step. You forward, you broadcast these to the second level LSTM in ELMo, and eventually you obtain, through this exercise, the key 3 ingredients that you need to calculate ELMo I task. So here it's important that you relate this slide to the previous slide, where we have ELMo I task, and ELMo I task I explained before. And I explain it again here, just a little bit more concise. ELMo I task is a function of the embeddings Ri, which are the raw embeddings in ELMo, the first bidirectional LSTM hidden states, and the second bidirectional LSTM layer hidden states, plus these 4 task-specific parameters, gamma task and SL task. And this comes out of your, let's be specific, HIL. HIL comes out of running your target text to ELMo, the pre-trained ELMo, here. You get HIL. From running your target text through ELMo, and then you can basically add the ELMo output as auxiliary embedding, which you see here, to obtain this E tilde I, this new, this augmented, this pimped embedding, if you wish, for your target test. When you do that, however, I put HIL here for a reason. I put HIL next to my pre-trained language model. I did not put ELMo I task. And the reason I did that is ELMo I task has these task-specific parameters. Its calculation entails these task-specific parameters theta task. I'm needing some other color. This guy here. And these are just scalars, so just weights in the averaging. And the weights are calculated when you train your target model. And in this way, the averaging mechanism that is part of ELMo, the averaging mechanism in which ELMo calculates this contextualized embeddings, ELMo I task, that requires averaging, weighted averaging, and the weights are trained on your target data. And in this way, the averaging is geared toward your target data and toward your target task. That's just another way why ELMo embeddings are contextualized and task-specific and are able to adapt to the target task. And that's a really important approach, because the whole context of this part of the lecture is NLP transfer learning. And you achieve adaptability to your target task by introducing these task-specific weights that are trained in an end-to-end manner as part of the target model, and not pre-trained. When you run ELMo to your target data, you obtain HIL, HI1, HI2, HI0. That is what you have. And in order to aggregate that, you need the weights for the weighted averaging, you need gamma task, you need SL task, and these scalar weights are trained on the target data end-to-end in your target model. Whereas the rest of ELMo is not altered at all. These are fixed. That's the idea. And this is how it's contextualized. You've seen how it's deep. That's ELMo, really. That's it. That's it. And yeah, I believe it's a very clever approach. relatively easy to understand. And if you read the paper and go to the website of the Allen Institute looking for some more recent benchmarks, ELMo has shown very good results. By the time of it coming out, it was top of the field, I believe. You have this analysis that they did in the paper where the authors applied ELMo to a couple of standard NLP tasks, these SQUAT or SNLE or SRL, CoRev, NER, sentiment. There are a bunch of standard data sets from different branches of NLP on which researchers compare themselves. And in the table you see what was the previous state of the art. Typically these numbers represent accuracies or F measures, some performance value in a nutshell. And you have the previous state of the art. Then the previous state of the art comes from some paper. And if you do your own paper, you can try to replicate what previous studies have done in the best way possible. But typically there is some variation. So this number is a number that, let's go here. This number is a number that was reported in the Chen et al. 2017 paper, and then implementing the approach or re-implementing the approach of Chen et al. 2017, the authors of the ELMo paper achieved this performance, slightly worse than what Chen et al. Have reported. And again, such variation is normal. When you do a paper, when you report a model, there are different sort of tweaks that you apply, and a single paper is just not enough to report everything that you have done. And because of that, other scholars will not be able to replicate your result with 100% precision. But as you can see here, they're getting very, very close. They're on spot. The data is also standardized. It's very fair, very rigorous comparison, and you see how ELMo basically pushed the baseline a little further. Quite consistently, if I put this flat, they beat every baseline representing the previous, top performer. Other papers show similar results. So that's not too unique that you basically outperform the state of the art in a variety of previous tasks. That's actually quite common with famous NLP papers like the ELMo paper. But certainly they had very good results to show. And what's quite interesting is that then doing some further analysis, they were able to showcase, let's say, it's not a proof, it's empirical evidence, how the two different layers in the ELMo architectures really pick up different things. Different patterns in text, in language. The lower layer, it was showing better performance on more syntax-oriented tasks like POS tagging, for example. You can, if you wonder how did they do this analysis, remember that the ELMo embeddings just enter some target task using this weighted averaging mechanism. And in this weighted averaging, I was saying that you normally train these task-specific parameters, gamma task and SL task, you train them, but you don't have to train them. You could also just set some of them to 0. You could, for example, set the weight of the second ELMo layer embedding to 0, basically ruling this out, and then approaching the target task with the first LSTM layer ELMo embedding only as auxiliary input. This is how they did that. And they found that the first LSTM layer picks up on syntactic patterns, whereas the second layer is better at picking up semantic patterns in data. So the two layers in their deep directional language model were exhibiting some task sharing, some job sharing behavior, one specializing on syntax, the other specializing on semantics, and that is certainly a great result. This is really what you want. And it further confirmed how ELMo is a good way, maybe the best way at the time the paper came out, to do NLP transfer learning. And it was really, again, maybe you remember my motivation that in deep computer vision models, you have different layers, learning different things, earlier layer learning edges, then later layers learning slightly more complicated geometrical shapes like squares or triangles, diamonds, and higher layer learning more abstract patterns like noses, eyes, mouth, and yet deeper layer learning than to aggregate this information into a face. This type of task sharing. The ELMo authors could also showcase that for their model, but for NLP, which is quite remarkable, I find. All right. And if you want to play around with ELMo, I'm afraid that we will not do that in the practical. It just goes too far. We are already in a part of a lecture where we can no longer really redo everything in the practical. I regret that, but it's just not possible. That's the type of task that you might find in the information systems seminar, which I offer every winter. That's where I let students work on more advanced NLP tasks, typically. And but you also found tons of examples online that would help you to get started. For example, if you consider using ELMo as part of the assignments, which is your choice. You can do that, you don't have to. If you decide to use it, then just note that on the ELMo website, you find a bunch of pre-trained embeddings, small ones, medium, or the original really big ones. More accuracy, more data, more runtime. That is the trade-off here. I'm sure that the table is outdated and that if you go to it today, you'll have even more options, what type of embeddings from ELMo you can download. The code to then put everything together you will also find online, so it's not too complicated. It's maybe a day of work or two in order to have your ELMo model up and running. Resources, as usual in NLP, being a bottleneck, but I would imagine that if you want to play with ELMo using Google Colab, everything should work out just fine. All right, and that was it with ELMo. Thanks a lot, and let's look into another idea to carry out NLP transfer learning.